So
I missed one day and look what happened.
yeah. Volume of revolution. What we're going to now use integration for is to figure out volumes. We already know that integration can give us an area under a curve. Okay? So the idea that was going to happen right now is if you take the area under a curve and rotate it 360 degrees, can you see that that would fill a solid shape? Okay? So right now, I've got from A to B with this curve, and since we're so used to using crayon, that's the area under the curve from A to B. Now, if I took that area and rotated it 360 degrees, it would fill in the volume of that shape. So what we're going to do temporarily, though, before we do the whole area, we're going to think about just this single line at A. If I rotate this single line 360 degrees, can you see that that would make a disk? Yes. Okay? If you just took that radius and rotated it 360 degrees, it would make a perfect circle. Yes. Yes.
You took the volume and you rotated 360 degrees when you fill a full shape plus that volume.
Well, if you took a volume and rotated it, it would just sort of like stay the same, would it not?
It's not a liquid. Not a liquid volume.
But what?
Okay, well, what are you saying? Are you saying like
So we're taking this slice that's shaded in orange, and you're taking that slice, and you imagine rotating it and filling in everything as you rotate it, the space that it takes up.
filling in the surface area?
Filling in the entire volume. So if I had just a straight line, okay, if I just had that straight line, and I said the area from 0 to 3, okay, that would be that rectangle, right? Now, if I took that rectangle and rotated that rectangle around the x-axis 360 degrees, that would do this, right? This, you wouldn't actually see, this line would not be there, okay? And yeah, and as you rotated it, whatever it's touching is filled in, okay? So that would create a volume. Now, if we look just at one little section, if I just take the straight line at A and rotate it 360 degrees, I would get a circle. And then if I moved over a little bit and rotated that one 360 degrees, I'd get another circle. So one of the things that we can kind of relate to is, you know, the volume of a cylinder is pi r squared times h. Pi r squared because that's the circle on the bottom, and h because you're stacking all those circles all the way up to fill the whole volume. The only difference in this shape now is the circles are changing size as you go. Right? If I would take this loudspeaker horn, well, if I would take that loudspeaker horn and put it on end, can you see that you've got a big circle and then a little bit smaller circles? As it goes up, the circles are smaller. And if they stack them all up, you would get your volume. But instead of a cylinder where we've got pi r squared times height, where it's just same shape all the way through, and that's why it's pi r squared times height, with this shape, our radiuses change. Well, how do we define our radiuses as you go along? Our radiuses are always our y values. And our y values are determined by our function. Okay? So, if we wanted to add up all of those circles, just like we do here, all the circles times by the height, what we do now is the same thing. All the circles, the height is just our function. The circle will be pi r squared. The radius is whatever the y value of the function is. And if we integrate that, we get that area, that small area, down to the radius. And if we do the circle and add all those circles together, we get the entire volume. Which is really cool.
It is.
And then what we can do further on is we can take one volume and subtract another volume, and then you can create all sorts of interesting formulas. Like if we look at the blue and the yellow, okay? What I'm doing is I have two functions, one subtract the other. That would give me the area between two curves. If I then rotate that 360 degrees, I get the area of this shape with this shape in the middle taken out. And what would that make? It's like, oh, there you go. You've got a volume of a Bell formula. Can you see the Bell? Can you see the Bell shape made? Without the inside, right? It's a perfect formula for a bell.
Except
Of a certain thickness. It can have different thicknesses all the way through, and you can figure out the volume that way. Pretty cool. Okay, so let's start off with some easy questions. Well, not easy questions, but learning how to use this formula. Find the volume of the solid that is generated when the region under y equals x cubed from 1 to 2 is rotated in the x-axis. So what we're going to do is we're going to draw a diagram of this. Here's our x cubed graph. You've got the point 1, 1, and you would have the point 2, 8. So this is the area underneath that curve. There's that area. Now what we want to do with that area, because that area will represent a whole bunch of radiuses, we want to do a revolution 360 degrees around the x-axis. So I'm going to just sort of estimate the same height there, same height here, and then you can sort of draw circles on there. And that's the shape that we would get. As far as coloring these shapes in, to help you see the shape better, I like to color the side of the shape in one color. So I'm going to color that in red and the end of the shape in a different color. Yeah, it's like art. Can you see the, gotta get rid of some of that orange. Can you see the volume now? It's like a UFO on its side. Yes?
Draw a circle from the top point to the bottom point.
Well, because, I mean, it's a three-dimensional object, right? This length here, which is 8, is the radius of that circle. So apparently this is 8 as well. It's just three-dimensional, farther. And I needed to make that 8 as well. It's kind of coming out of the page. I could take this shape and rotate it towards, if I grabbed it here and showed it to you, it'd be a perfect circle of radius 8 on the bottom. If I turned it the other way, this circle at the top would just have a radius of 1. Okay? So we've got a shape that's a perfect circle with a radius of 8, tapering down to a radius of 1. Okay? And we are going to figure out what the volume of this would be if the side of this shape follows the x cubed graph. So what ends up happening is we know the area of a circle is pi r squared. So what we're going to want to do is we're going to use that idea. We're going from 1 to 2. So we're integrating from 1 to 2 to show that our radiuses are changing as we go from 1 to 2. Our radiuses are always whatever our function is. In this case, our function is x cubed. And then our area of each of those circles is pi r squared. And so our radius gets squared. We could put the pi inside, or you can put the pi outside the function because it's a constant. And we're going to integrate with regards to x. The length of it, like this from 1 to 2, that shows up in the integration. So what I've created here is a way to add up a bunch of circles.
Looks deceptively simple.
It is deceptively simple. So if I simplify, this is going to be the integral from 1 to 2 of x6 to the dx. Add 1 and divide. From 1 to 2. What is 2 to the 7? 128. 128 over 7 minus 1 over 7 all times by pi. And whatever units we had cubed. Crazy. It is, as you said, deceptively simple. Whoever first came up with the idea, that is the hard part. And showing that that idea works for all shapes and sizes.
So whenever it says that the side of the region is rotated about the x-axis, that means that it's made
If it's rotated 360 degrees around the x-axis, it makes perfect circles as it rotates. So let's go to a classic. I'm going to go off. I don't know what the next question is here. Yeah, that one's not as fun. We'll do this. Well, it is fun, but we'll do one in between, something you've already done. Okay? Let's go back to related rate problems. In our related rate problems, we had gravel coming up a conveyor belt falling onto a perfect conical shaped pile. You remember those?
Yes.
And so here we go. Here's my conical shaped pile. Pick a radius, pick a height. Just 3 for radius. What do you want the height to be? 7. Okay. 3 and 7. What's the volume of this cone? What's the volume of a cone formula? 1/3 pi r squared height. So the volume of this one should be 1/3 pi 9 times 7, 21 pi. Okay? I'm going to take this cone on my x-axis here. I'm going to draw a line with this equation. Y equals 3/7 x. So if I decided to, at 7, put a point, how high, where would this point be? At 3. Agreed? 7, 3. So if I wanted to take this line and rotate it 360 degrees around the x-axis, what would I get? I'd get that cone on its side. No, this length is 3. This 7 represents its height. Okay? Okay. So now if we integrated this from 0 to 7, pi, the radius is always 3/7 x squared dx. What do we get? Let's find out. So let's plug this in. I'm going to get, well, first of all, I'll simplify this. From 0 to 7, this will be 9 over 49 x squared dx.
Yeah, you can take out the constant.
You could take out the 9 over 49. We're going to add 1. Add 1 to the exponent and divide.
Just cancel that.
From 0 to 7. Sure enough, these would simplify to be 3, right? What happens when I plug in 7? Is it all right if I tell you guys that when I plug in 7, this will be 343, but this is 7 cubed, this is 7 squared. They're going to cancel out and just give 7 times 3, and I'll get 21. And I plug in 0. Same answer. That's kind of cool. It should be. I mean, I just explained something, and if it didn't come out as the same answer, that would be really bad. But the power that we have right now is I could say to myself, well, I just randomly chose, well, Riley randomly chose 3 and 7. Right? The only way you can figure out this volume is if you've memorized the formula. If you've forgotten the formula, you're out of luck. But now, let's say we just randomly picked 3 and 7. We could have randomly picked any numbers. In other words, I could pick anything for R, anything for H. Those are just numbers. Well, what would my equation be if I picked anything for H, anything for R? What's the equation of that line? R over H, X. And then over here, I would have R over H, X squared. And just R and H are just numbers. We're just using variables to represent numbers. They're not functions. They're not functions of X.
R squared over
So we'll get R squared over H squared.
and X squared.
From 0 to H. Okay, now I'm going to erase the rest of this because it's... So let's integrate. Still have pi out in front. We'll get R squared over H squared, X cubed over 3 from 0 to H. You plug in H. H cubed over H squared is going to result in just pi R squared H, all divided by 3, is equal to volume. And there's the formula. We just made the formula. Instead of having to memorize it, we invented the formula. Or we took an idea to create the formula. So now we can say, are there any other things we could do that with? That we want to have formulas. Like if you knew the equation, of a semicircle, you could rotate it 360 degrees and get your volume of a sphere formula.
Isn't a semicircle that's half a parabola?
No, semicircle is not a half a parabola.
Parabola only take absolute value
Oh, I
and take that region.
So we would have to figure out what that equation is. And it's, well, this is,
X squared or whatever the radius is.
Negative.
here, if
Okay, that's actually
x squared plus y squared equals r squared gives you a circle around the origin. Okay? If you wanted to get y by itself, You'd square root both sides. The positive one would be the top half. And then you could integrate from negative r to r. Plug that in. You'll get your volume of a sphere formula.
4/3 pi r squared.
4/3 pi r cubed. But it's close,
Close enough, right?
right? Some very cool things can happen. So now let's go to an actual different shape. Because you can take this idea with any shape and figure it out. So what would happen if you had square root of x minus 1 is a square root graph shifted 1 to the right. There it is. There's your square root graph. If we were graphing it between 1 and 5, 2, 3, 4, 5, rotating that again, as far as color coding this, it is warmer in here today.
You made a mistake, it's not cold enough, Mr. Ross.
We just, oh, this is the Christmas ham function.
Oh, I'm hungry now. It's not good.
I advise drawing them to get a sense for what you're doing. You're going to find out sometimes where things are at based on that. So now we have to figure out that volume.
I got 0.
You got nothing? If you go buy that ham and you end up bringing home nothing, you're going to be in trouble. So
Oh, I see.
we need to find the integral between 1 and 5, pi, our function, x minus 1 squared, dx. What's nice about squaring that square root? It just goes away. And we just get x minus 1 dx, which when we integrate x squared over 2 minus x from 1 to 5, set everything up, plug in 5, 25 over 2 minus 5, plug in 1, 1 over 2 minus 1. What do we get? 24 over 2, which is 12, minus 4. You okay with that mental math? See how I was able to avoid some fractions? And the volume is just 8 pi. Very cool.
8 pi.
So now,
Units cubed, yeah. Thank you. We got the units cubed, Mr. Ross.
yeah, u cubed.
No, where U equals units.
Where u is equal to units.
I put U using Michelle as a mark.
So let's draw and see what this shape is going to be. It's going to be a beautiful shape. We want the region between sine x and cos x from 0 to pi over 4. So if I draw sine x here in green, I'm going to spread things out a little bit here. Get a nice looking graph. Now, I'm going to put 2 pi on here. This would be pi. This would be pi over 2. Pi over 4 then is only right here. So it's a little section of this. But the reason I drew all of this is so that I can draw my sine graph completely up to 1, down to negative 1. There's my sine graph. I'll draw my cos graph in black. Cos graph starts at a maximum. And of course, these two graphs intersect at pi over 4. Now, I'm going to want to take this area that's between them and rotate it 360 degrees.
So that's just a tiny area.
Okay? So that's going to be, I'm going to take this point here, do this in red. This point here in red is this distance, so that same distance there, and draw a circle. Okay? I'm going to take this point here and this point here and draw a circle, but not draw the other part. Okay. I'm going to draw that line in there in green. Can you picture a dog dish? Okay, a dog dish on its side. It's a dish with a hole. Okay, it actually, like, oops, I'm going red here. Here's the bottom of the circle. This dog dish has a little tiny flaw in it because right on the bottom is a tiny hole.
You don't need it.
Right? Now, that hole theoretically is smaller than a water molecule. So you could still fill it with water, and even though there's a hole in it, it wouldn't leak. But there would still be a hole in there.
That doesn't matter. If you can't see it, it doesn't count.
Because it's just single, the hole at the bottom is a single pixel kind of a hole.
But a hole of water is smaller than a pixel, I thought. So they draw it as a single pixel.
Can't draw a picture.
Yes, you can. Exactly.
They're so small.
Oh, you filled it up then. It's too big. So this is what we want to find the volume of. We want to build this beautiful dog dish based on our two favorite trig curves for our dog, and we want to make it out of titanium. So we need to go buy some titanium and figure out what volume of titanium we need to buy first in order to make this dog dish.
I have some questions to ask you.
Just to make this work for us, there's our titanium. Is that the right color for titanium?
That's too light.
Too light? Need a little bit of more.
It needs to be dark, like the soul. Like the soul.
There we go. There's the side of our beautiful titanium dog dish.
No, it's cheap.
Would you agree that we need to find from 0 to pi over 4 if we figure out the volume of the upper function, which has a radius of cos?
So you forgot the pi over 4.
Thank you. That would be the area of our upper function. And then we're going to need to subtract from 0 to pi over 4 of our bottom function. We have this. Does that make sense? Can you visualize if this is the volume of the whole thing filled in, and this would be the volume of the space taken out? If you take one volume and subtract the other volume, you would get just the dog dish that's left. The sine x part is the inside, which is the space for the water.
So you're making it out of solid titanium.
We start off, the rest of it is solid titanium. You love your dog, so you're willing to spend this. Okay? What's the problem with each of those integrals?
Well, what do you mean?
Can you integrate cos squared x easily?
No.
No,
It's alright.
because it's a chain rule. Cos squared x is a chain rule. Not easy to integrate. Sine squared is a chain rule. But you have another function in there, so that causes a problem. You can't divide by another function because then that ends up causing you issues.
Divide by the integral of sine is negative cos, so you get negative 10.
Doesn't work. Try it and then derive after, and it'll all go to.
Is there a reason that doesn't work?
So you want to integrate just cos squared dx, and you want to add 1 and divide, and then the derivative of cos is sine. But right, the derivative of cos would be sine, so you want to divide by sine.
Cotangent. No. Wait.
Cotangent times cos squared
Yeah. Cotangent cos squared.
plus c. This is what you want to do. Okay? Take the derivative of this. What would you have to use? Quotient rule. If you use the quotient rule, would you get a sine squared on the bottom?
Yeah.
Where's that on? Okay? This is bad. This does not work. Because when you try to check to see if it works by doing the derivative, because you can divide by a constant, no problem. That's just a number. You can't divide by a function because the dividing by a function causes problems with derivatives. You'd have to use substitution, but there's not, if you let u equal cos, there's no du in this formula. Okay. So, we've got a problem. We got a problem. We go back to this. We can't integrate this by itself. We can't integrate by this itself. However, we can, we can factor out the pi out of the whole thing, and then we would just get the integral from 0 to pi over 4 of cos squared x minus sine squared x. Because we have a property of integrals that if you add or subtract integrals, and that's cos 2x.
Yeah, because you just divide by 2
And cos 2x, we can do the integral for. The integral of cos 2x
is divided by 1
is sine 2x divided by 2 from 0 to pi over 4. What happens when you plug in pi over 4? What's sine of pi over 2? 1. So we get 1/2. What is sine of 0? Not anymore because we use the identity. And then the amount of titanium you need to go out and buy for your fancy dog dish is pi over 2 units cubed. Fascinating.
Why do you do cos squared, subtract the sine, like this start?
Why do we do the cos squared, subtract the sine squared from the start?
I'm saying like the volume.
So if I just did the cos squared,
So the volume of the cos graph.
that would be this, I'll color that, that's this dog dish that's solid. Last time I bought a solid dog dish is awful. You pour water, it just hits the top and falls off the side. Dog is always thirsty. It's just, water is always on the floor.
So it's just the inside.
It's just the solid part. Okay?
So even the outside.
And then the sine squared part is that solid thing, the inside. So if I take the volume of the whole thing and subtract the volume of the inside, what am I left with? The dog dish with the opening.
Why is the sine on the inside and the other one, does the other one contain the entire thing solid?
This first one here with the cosquared is the entire thing solid. This second one with the sine squared is the entire thing solid with the red and the green. And if I take that solid red and green out of the whole thing, I'm left with that dish with an actual place where I can put water, with the tiny pinhole at the bottom, but it's okay. Well, because right at 0 is where sine is touching right at 0. So you're removing that.
Because you're doing a value minus value, right? Because there's a hole. Because if you're going this for the sine graph, you notice the line goes down.
This is a good spatial brain exercise.
And you notice at the same time, look, you see cos. What's the answer? You see sine starts here and then goes up, right? That's the point. There's nothing there. There's no area. I actually got at 0. 1 pi. You rotate around the x-axis. Same thing. Teach him.
Good? So really fascinating way that you can also subtract to. And then this is similar, like with subtracting, you can now, if we go back to our original picture, you can now imagine I could take the entire volume of the upper function and subtract the entire volume of the inner function. And what I would be left with is the volume of that bell. Now I'm going to give you, oh that was bad, give you time to try some of these. So turn to section 11.7.